Welcome to this product presentation on the overview of Integral MetaFSI. This presentation is going to talk about what MetaFSI is, the motivation behind developing MetaFSI, and how it helps us introduce a new level of multidisciplinary analysis and design capability when used in conjunction with CFD++ and CSM++. What is MetaFSI? MetaFSI is Metacom's in-house fluid structure interaction suite of tools designed specifically to work seamlessly with CFD++ and CSM++ to carry out fluid structure interaction or FSI analyses. MetaFSI plays a key role in enabling tightly coupled fluid structure interaction capabilities. And to help achieve this tight coupling, MetaFSI performs the following primary functions. It computes the loads from CFD++ solution and transfers them to CSM++ or other third-party structural mechanics solvers. It helps the user set up and test the CFD mesh morphing process with various advanced options providing fine-grained control to ensure robustness while minimizing the computational cost of the morphing process. And finally, MetaFSI carries out the CFD++ mesh morphing based on the displacements computed by the structural solver and options specified by the user. To cater to a wide user base, MetaFSI is made available in two versions. A version that's built in to CSM++ or structural mechanics software, or a standalone version designed to work with third-party structural solvers such as MAC-NASD. When using with CSM++, MetaFSI is automatically activated when the user checks the FSI option when setting up an analysis. MetaFSI simply appears as a new page in the CSM++ notebook alongside the geometry and model pages. This enables a tightly coupled FSI setup process with an easy and consistent user experience. The MetaFSI standalone version enables users of MAC-NASD to easily run FSI analyses by coupling with CFD++. In this version, MetaFSI provides the user with nearly identical capabilities and setup process as the built-in version. Let us now give you an overview of the complete FSI process when using Metacom's suite of tools, CFD++, MetaFSI, and CSM++. MetaFSI initiates this process by communicating with CFD++ and CSM++ to receive information about their respective wetted surfaces and other relevant information, such as timestamps. It then instructs CFD++ to solve for pressures and stresses, which are then sent back to MetaFSI. MetaFSI, in turn, computes forces and moments from the CFD++ solution and transfers them onto the CSM++ structural grid. Next, CSM++ is instructed to compute displacements based on these forces received, which are then again sent back to MetaFSI. And finally, to complete one FSI iteration, MetaFSI takes these displacements received from CSM++ and morphs the mesh as per the options specified during the setup process. This morphed grid is sent to CFD++ again, and this whole process is repeated, depending on the type of analysis, until some convergence criterion is satisfied or for a specified number of time steps. Before we proceed further, we'd like to introduce the user to the Integral MetaFSI Advanced User Interface, or the AUI. The AUI is part of Metacom's Integral Computational Multiphysics Framework, or ICMP. The AUI enables us to provide a single environment for mesh generation, CFD, structural analysis, and visualization of results. This is possible because of a shared design language and user interface between all ICMP-based products. It helps us deliver an intuitive and simple guided problem setup process that is simultaneously powerful and user-friendly. Some of the features of the AUI include a menu bar, a toolbar, a canvas to display the CSM and CFD meshes, a notebook, and several pages within the notebook. When used with CSM++, MetaFSI appears as a page alongside the geometry and model pages. In standalone mode, MetaFSI will be the only page in the notebook. Within the MetaFSI page, information is organized in trees. Here we have the action tree, which provides options regarding the setup and testing of the mesh morphing, and the boundary tree, showing a list of all CSM and CFD boundaries. Every item in the action tree is called an action item, and every action item opens a corresponding action panel. As the user completes each action panel and moves to the next, a status indicator next to the action item shows whether that panel has been successfully completed with the green check mark, or if the user needs to pay attention to some of the options in that panel, shown with a red X mark. The AUI allows the user to customize the user interface according to their preferences, with panels that are dockable and resizable. And finally, this ICMP-based framework also makes possible an intuitive problem setup process, guiding the user in a logical manner with a thinking engine that adapts the action tree items based on the selections made previously. Let us now explore some of the capabilities of MetaFSI by starting with its most important function, mesh morphing. In the morphing process, we would like to take displacements at the wetted boundaries and propagate them into the CFD++ volume. This can be thought of as consisting two stages. The first simply involves computation of 3D displacements by interpolation. These are the displacements that need to be applied to each grid point and are computed with the help of 3D radial basis function-based or RBF-based interpolation functions, with the global support to ensure robustness of the algorithm. The second stage of the mesh morphing involves actually moving these grid points using the previously computed interpolant. Using RBFs with the global support typically results in an algorithm that's computationally expensive. To substantially reduce the effort involved, the user is provided with options such as restricting the active morphing region to a user-defined subdomain and other techniques that will be discussed shortly. Now, for most problems involving fluid structure interaction, it's common for the CFD and the CSM meshes to be dissimilar, with each mesh optimized for its respective solver. However, MetaFSI is capable of working with such dissimilar CFD++ and CSM mesh surfaces. The exchange of CSM displacements and CFD loads are done by nearest neighbor interpolation, and this transfer is made such that the total load and the center of pressure are preserved. Here we see the CFD boundary of a 3D wing model that is set up to exchange loads and displacements with the corresponding CSM boundary modeled as a 2D shell. It is clear that the two meshes are only collocated to a certain degree, but enough for MetaFSI to carry out the mesh morphing. Now, as previously mentioned, MetaFSI is built into CSM++, but it's also available as a standalone version if the user wishes to use a third-party structural solver such as MSc Nastran. While the vast majority of the features and capabilities of MetaFSI are shared between the two versions, there are advantages when using with CSM++. Firstly, using MetaFSI with CSM++ provides a consistent and integral user interface for the problem setup process as opposed to having a varying user experience when using Nastran. Using with CSM++ also allows the user to visualize the CSM and CFD boundaries simultaneously in the AUI, which can be critical to check for their degree of collocation. This visualization is currently not possible with Nastran. Other capabilities that are made possible by the integration with CSM++ include moment transfer in addition to force transfer, utilizing rotational degrees of freedom, and additional relaxation options during displacement transfer. Finally, using MetaFSI with CSM++ also enables the use of additional solver types, such as normal modes-based coupling. Let us now explore this important capability in a little more detail. For a transient analysis, CSM++ gives the user the option of running a modal analysis. With the help of MetaFSI, the same capability is extended to a transient FSI analysis. Here, MetaFSI pre-computes the morphed mesh corresponding to each of the structural modes and constructs a linear combination of these meshes for each time step, based on the appropriate generalized coordinates determined at that time step. This significantly cuts down on the computational time of the morphing process. The benefits of the ICMP approach can be readily seen here. Checking the box for a modal analysis in CSM++ automatically activates modal morphing within MetaFSI, just as the user might expect it to. Some additional capabilities of MetaFSI include the ability to specify independent physics options in CFD++ and CSM++, a choice of implicit or explicit coupling, a choice of serial or parallel mesh morphing for significant speed gains, and features a robust sockets-based communication between CFD++, CSM++, and MetaFSI. And finally, MetaFSI has the ability to correctly transfer loads from CFD boundaries to reduced dimensional structural boundaries, such as beams or shells. For example, it's common to model a wing structure as a beam. With MetaFSI, proper load transfer between the beam model and the CFD surface is ensured. We shall now cover some of the basics of using MetaFSI. The first step would be to choose which regions in your CFD domain are expected to morph and which aren't. This is done by assigning each CFD++ boundary as either fixed or movable. From now on, we shall refer to these boundaries as anchored and wetted. MetaFSI also allows for a third scenario, where we would like certain boundaries to simply rigidly follow the motion of the wetted boundaries, such as nacelles attached to wings. On the canvas, points on the anchored boundaries are visualized in white, while the wetted points appear in turquoise blue. The second step is to optimize the morphing process. Calculating interpolants and morphing the entire CFD grid is computationally expensive and typically unnecessary. We should find a way of reducing these computations involved while adequately morphing the grid. This can be done by what is called control point coarsening. Here, we limit the morphing process to a subset of grid points in the active region, which we call control points, and are determined by defining custom density regions to manage the spatial variation of these control points. The extent of coarsening that strikes a balance between reduced costs and adequate mesh morphing varies from one problem to another. The final step is to run test deformations before an actual FSI analysis. This can be helpful to refine the control point coarsening options and in general to simulate and verify expected morphing behavior. The user can prescribe an analytical displacement field or provide an existing CSM++ solution to test the morphing. If MetaFSI encounters negative volumes during the process, the corresponding cells get highlighted in the AUI, letting the user know where to tweak their coarsening settings. Let us now look at some examples showing the morphing process. Here's a two-dimensional example of morphing involving an airfoil. The outer boundaries of the grid are anchored, while the airfoil boundaries are prescribed a motion. As you can see, MetaFSI effectively morphs the mesh while preserving its overall structure. Next is a 3D case involving the motion of a wing flap. The animation below shows how the mesh is morphed to follow the motion of the flap. Finally, this is a case where MetaFSI was used for a significantly larger CFD domain. This is a mesh provided for the AIAA drag prediction workshop and contains nearly 34 million cells. MetaFSI is able to morph this mesh to accommodate for a tip deflection of over 20% of the wing half span, while maintaining the integrity of the mesh. Beyond the basics described so far, MetaFSI is also capable of some advanced features, a few of which are mentioned here. The first is deformation ramping. Sometimes during morphing, it is beneficial to morph the mesh gradually over a specified ramping zone to avoid negative volumes. MetaFSI provides options to specify piecewise linear, independent ramping factors along the X, Y, and Z axes. For example, this capability can be useful when a cantilevered boundary condition in CSM++ is not exactly at the same location as a rigid CFD++ boundary condition. Another advanced feature offered by MetaFSI when used with CSM++ is displacement relaxation. Here, it's possible to modify the interface displacement sent to the morphing routine and relaxing it by taking into account displacements from previous subcycle iterations. MetaFSI offers two relaxation techniques, interface quasi-Newton or IQN and the dynamic or Aitken relaxation. This capability is critical for certain applications involving highly flexible structures. MetaFSI has the ability to use an intermediate mesh to transfer loads coming from the CFD++ wetted surfaces. This is an optional step that can be used to improve the reliability of the load transfer to the actual structural mesh, and can be especially useful when working with complex 3D CFD meshes and a 2D structural model. Let us look at one final advanced feature of MetaFSI, and that is control point augmentation. When the user defines a morphing region and determines the density of control points contained therein, they also have the option to augment or even replace, if they desire, the CFD anchored and wetted points. Depending on the problem, this can help speed up the mesh morphing significantly or can improve its reliability and the reliability of the load transfer. This is achieved due to a well-conditioned RBF interpolation. Now, let us look at a few validation cases where CFD++, CSM++, and MetaFSI were utilized in fluid structure interaction problems, starting with the HIRENASD wing. This is a 3D aeroelastic wing with a generic fuselage model for which a Nastran structural model exists. Here, we have used the ability of CSM++ to import a full Nastran model, not just a mesh, to run an FSI analysis. This is a solid model involving parabolic tetrahedrons, point masses, and rigid elements. The model is made of steel and is subject to periodic excitation close to its second natural frequency via axial forces applied to the root to mimic internal force couples. Two kinds of analyses are performed, a steady state and a transient analysis, at a Mach number of 0.8 and a Reynolds number of 7 million. The wing model sees an angle of attack of 1.5 degrees, and for a transient analysis, the load is tuned so as to provide 2.4 millimeters of displacement at a certain accelerometer near the wingtip. First, to verify the model, the eigenvalues were determined by CSM++ and are provided here, along with comparisons with experimental results and Nastran results. Visualizations of some of the mode shapes are also shown here. Experimental results are provided in the form of CP data extracted from probes at several sectional locations at 7 different span-wise stations. For a steady-state analysis, it is clear that CFD++, CSM++, and MetaFSI provide a solution that closely matches these experimental results. For the transient analysis, the magnitude and phase of CP at the same locations, computed with respect to the displacement at an accelerometer location, are compared again with experiment. The results match very closely for most of the span-wise locations, with some discrepancies appearing near the wing root. This can be attributed to the use of a relatively coarse mesh. An animation visualizing the solution of the transient analysis is shown now. The second validation case is a flutter analysis of a 15-degree swept-back wing in a subsonic flow. The geometry of the wing model is shown below, along with locations where the displacements are monitored. The experimentally determined flutter point is at Mach 0.45, and an available Nastran solution computes the flutter point at Mach 0.455. The flutter point determined by CFD++, CSM++, and MetaFSI comes out at Mach 0.475. This is a slightly higher result and can be improved by using a finer CFD mesh near the sharp edges of the wing. The plots here show the perturbation response of the wing at Mach 0.47 on the left and Mach 0.48 on the right. Slight differences are also noticeable between using an explicit and an implicit coupling strategy. The third validation case consists of a two-dimensional laminar flow in a square cavity with a flexible membrane at the bottom, modeled using large strain elements. An oscillatory horizontal velocity is set on the top wall and at the flow inlet at the upper top corner. An animation showing the deformation of the membrane over time is presented here, along with comparisons of other results from the literature. And finally, let us look at another 2D numerical benchmark proposed by Turek and Hran. Here we have an incompressible laminar channel flow around a cylinder to which an elastic bar is attached. The velocity profile at the left channel inflow is parabolic. The cylinder is intentionally slightly off-center along the vertical axis to prevent the dependence of the onset of any possible oscillation on the precision of the computation. An animation showing the time history of the oscillating elastic bar is presented here. The quantities for comparison include the lift and drag forces exerted in the cylinder and bar assembly, as well as the deflections at the tip. From these results provided, it is clear that CFD++ and CSM++, together with MetaFSI, are able to match results by Turek and Hran. It's worth noting that this FSI analysis requires the use of the iterative quasi-Newton or IQN displacement relaxation to yield an accurate solution. To summarize, MetaFSI is Metacomp's in-house FSI suite of tools that are designed to enable tightly coupled fluid structure interaction modeling by working seamlessly with CFD++ and CSM++ or other third-party structural solvers. The primary functions of MetaFSI are to set up and test the mesh morphing, transfer loads and displacements between CFD++ and CSM++, and more importantly, to morph the CFD++ domain based on the computed CSM displacements. We have seen that MetaFSI is part of Metacomp's integral computational multiphysics framework that enables a unified, intuitive, and simple problem setup process that is simultaneously powerful and user-friendly. We've given a brief overview of the basics of what goes on during the morphing process and all of the various options available to the user to optimize and test out the morphing process. We've presented some additional capabilities of MetaFSI, such as the ability to work with MSc Nastran, work with dissimilar CFD and CSM meshes, and integrate with CSM++ to run a transient modal analysis. We've also looked at some of the advanced features supported by MetaFSI, such as displacement relaxation, deformation ramping, and control point augmentation. Finally, we've provided a collection of 2D and 3D validation and benchmark cases using CFD++, CSM++, and MetaFSI to provide a glimpse of the kinds of analysis and the quality of results users can expect when running FSI analysis. Thank you for your attention. For more information on IMetaFSI or other Metacomp software products, please contact info@metacomptech.com.